All right, we'll continue here. We want to take a look at the barometer here. Basically, the barometer, the outside of it is open to the air, and so you have the weight of the air on the outside, but on the inside, is there any gas in this tube here? No, there's no gas in this tube, and so you got a lot of air, and in fact, you know, what is the weight of the atmosphere at sea level, approximately? How much does the atmosphere weigh at sea level? One atmosphere, or in terms of pounds, how many pounds? 14.7 pounds per square inch. And so we have this constant burden, although we don't know of it as a burden because it feels normal to us, right? It feels normal to be under 14.7 pounds of atmosphere. The thing is, if that 14.7 pounds wasn't there, you know, then it would feel very abnormal. That's what we'd call a vacuum, because if we start removing some of that weight, well, we would know that. And the vacuum is anything less than 14.7 pounds. So if we had 10 pounds of atmosphere instead, that would feel like a vacuum to us here. Although, you know, as you go up higher and higher in elevation, the weight decreases, so the pressure becomes less. But at sea level, 10 pounds would feel like a vacuum. So here, what we can do is we can just weigh. So if this is 14.7 pounds of air, then this must be how many pounds of mercury? This column mercury must contain 14.7 pounds per square inch. That's got to be 14.7 pounds per square inch of mercury here. So the two pressures would be equal. The pressure here we call the gas pressure. The pressure here, which we call the liquid pressure. Now liquid pressures are kind of odd in a way, because it's not just weighing a bunch of mercury, you know, and then saying, you know, because if we're looking at these would all be different masses of, right, of liquid, you know, from this would be the least and this would be the heaviest. But all of these liquids exert this exact same liquid pressure, which is odd. The liquid pressure just depends on how tall this column is. That is the height of this column. And so the thing is, you know, if you think about it, like if you go swimming in a small swimming pool, if you go swimming in a small swimming pool, you're 3 feet deep versus the ocean. You know, if you go in the Pacific Ocean, you're 3 feet deep. You know, 3 feet depth in the Pacific Ocean versus 3 feet. Well, you got 3 feet of the Pacific Ocean above you. Shouldn't that just crush you to death compared to a small pool? No, in fact, the two pressures are going to be the same. And so what it does is liquid pressures are going to depend on the height of this. And there's some physics involved here, because when we're looking at the pressure, and I'm skipping all this, you know, but essentially the pressure of a liquid is equal to G. G is the gravitational constant, you know, in physics is 9.8 meters per second squared. And so it's the force of gravity times H. H is the height, you know, or the depth, times D. D is the density. And so we're going to take, you know, the gravitational constant around sea level, or, you know, where we are, and Earth doesn't change that much. You know, it changes a little bit, but not significantly. And so we're going to take G as a constant, and D we're going to say is a constant, even though the density will vary slightly. You know, the deeper you go, the more dense it should be, but it's minimal, especially the changes that we look at. And so if G and D are constant, then the pressure is directly proportional to a constant times the height of the column. And so when we're looking at liquid pressure is technically GDH, but we're just going to call it H because that's easiest. It's easiest to take a ruler and just measure the height of this column here. Now, we don't use water. The reason, does somebody know why we don't use water to measure barometric pressure?
Too tall.
Yeah, the column would have to be too tall. You know, to get 14.7 pounds per square inch of water would require a column about 3 feet, not 3 feet, 3 stories tall, more like 30 feet tall, you know, roughly. And so water is not very dense compared to mercury, and so, you know, we just need this huge column. So atmospheric pressure would weigh this down and then push up the water, you know, approximately 30 feet. We can calculate it. This is a fairly simple calculation to do. Let's calculate it. And so whenever we record pressure, you know, we're saying that pressure is equal to a constant times the height of the liquid. We can use any liquid, you know, but it just makes more sense to use mercury. There are water barometers and water manometers, this kind of stuff. Mostly water manometers. But a constant times the height of the liquid. So if you look at the at your gas, if you have natural gas at your house, you know, what is the pressure coming? The pressure they usually measure in terms of gauge pressure. You guys know the difference between gauge pressure and absolute pressure? Exactly. And so the gauge pressure of the gas coming out of here is about 4 to 8 water inches, they call it, water inches. That's the pressure. And so let's look at that. Let's see what we're going to do here. We're going to do 2 calculations. One calculation is, let's say you have a natural gas, you know, nat gas coming out of here. And the nat gas is, let's go with 8 inches of water. 8 inches of water. What is the absolute pressure of the natural gas coming out of the building, right? In terms of atmospheres or millimeters of mercury or whatever. In terms of what we're normally thinking. All right, so this is the house. Yeah. Okay, so we need to measure the barometric pressure of this day. Let's just keep it simple. We're going to say the barometric pressure is 1 atmosphere or 760 millimeters of mercury liquid. And so we have 2 different liquids here. We have water liquid and mercury liquid that we're measuring pressure. Well, we just can't add those together. We have to make sure that they're the same. And so what we need to do is we need to either convert mercury liquid to water liquid, or we convert water liquid to mercury. And what we'll do is we're going to convert water liquid to mercury. And so if we have 8 inches of water, that weighs a certain amount, right? How much mercury would we have to have in order to weigh the exact same amount as 8 inches of water? And so what we're going to do is we're going to just set the pressures equal. So what we're going to do is we're going to convert this from inches of water. We'll go from inches of water maybe to centimeters of water. From centimeters of water, we'll go to millimeters of water. And from millimeters of water, we're going to convert it into millimeters of mercury. You know? And so if I have this many millimeters of water, how many millimeters of mercury would weigh the same amount as that? And so, let's go from 8 inches to centimeters. Well, 8 inches of H2O liquid, converting that to centimeters, let me write this, 8 inches. 8 inches would be 2.54 centimeters exactly in an inch, right? And then going to millimeters, 10 millimeters exactly in 1 centimeter. And so now we have millimeters of water. Now, how do we go from millimeters of water to millimeters of mercury? How do you think we go there? Well, we could either, some people could do this in their head, other people will do it as a conversion factor, other people will do it algebraically. And so what we're going to do is we're going to do an algebraic approach here. So we're going to break in here and do an algebraic approach. The algebraic approach is going to be like this. The pressure in terms of liquid water, we want equal to the pressure in terms of liquid mercury. So we want the liquid mercury and the liquid water to weigh the same amount, right? But the height is going to be different, right? Because mercury is so much more dense than water. All right, so the water pressure is just equal to the constant. Well, the constant is, right, what is it? It is the height of the H2O liquid times G, which is the gravitational constant, times D, which is going to be the density of liquid water. But the liquid pressure of mercury is going to be the height of the mercury liquid times G times the density of mercury liquid. And so G, the gravitational constant, will be the same. And so the height of the mercury liquid that would be equivalent to the height of water is just going to be the height of the mercury liquid will equal the density of the mercury liquid over the density of H2O liquid times the height of the H2O. Oops, did I get that? Right. I'm the height, yeah. Oops, no I didn't. I'm trying to solve for the height of the mercury. So I just inverted it. Sorry about that. Let me redo this. It's going, the height of the mercury liquid is going to be the height of the H2O liquid divided by the, no, not the height. What am I doing? I can't read my own writing here. All right, we're solving for this. So it's going to be the density of H2O liquid over the density of mercury liquid times the height of the mercury liquid. That's correct. And so let's try to figure out this by getting the density of mercury, which, let's see, what is the density of mercury again? 13.7, was it? It's here in the book. Oh yeah, 13.5951, here it is. So 13.5951 grams per milliliter, or centimeter cube. Centimeter cube and milliliter is the same thing, but I'll just write milliliter since it's less writing. Over the density of water. Oh, what is the density of water? Were we given the temperature? We weren't given the temperature. We could assume a temperature and look it up, but you know what? Do I want that kind of precision? You know, what do you think the house gas pressure, is it that precise? Is it right on 8 inches, you think? No. And so I don't need that much precision. So I'm going to limit this. I'm going to call it 1.00. I know that 3 sig figs, this is true, over a wide range of temperatures. Now, if I want to go to 4 sig figs, this would be false, or 5 sig figs, for sure, false. But to 3 sig figs, I'm pretty confident of that. Now, what is the height? Well, what does this come out to? Can somebody tell me how many millimeters of water we have? Here. What is it? 203.2. 203.2 millimeters of water. So if I have a 203, or about 2 meters, actually this less, this 200, what would that be, 20 centimeters? About 20 centimeters of liquid water is equivalent to how many millimeters of mercury. And so the height would be 203.2 millimeters of H2O. Okay, the H2O cancels the H2O and leaves us with mercury. Grams per milliliter cancels, and how many millimeters of mercury is this? 14.9. All right, so we get this is equivalent to 14.9. Is that, well, that's all right. We have more digits than we're allowed. 14.9 millimeters of HG liquid. Can you give me one more? What's after 9? 4. 14.94.
Actually 5 and 14.95.
95? Did you round it? Don't round it.
I mean, there's a 6 after 4.
Then we'll just leave it at 4.
Okay.
14.94 millimeters of mercury liquid. And so that's what the gauge would read. You know, the gauge would have, a gauge would have 0. And then we are at 14.9 millimeters of Hg pressure. The gauge also, you know, a gauge can have negative pressures too. And so what would be the highest negative pressure that this could register, or the lowest negative pressure this could register? The lowest would be minus 760 millimeters of mercury, vacuum. It'd be pretty hard to get that. On Earth, it'd be pretty much impossible to get there because of vacuum leaks and other stuff. It's so hard to generate these high vacuums, but you could get quite a bit of vacuum here. That's the gauge pressure. The gauge pressure, you can have positive and you can have negative pressures. What 0 refers to is, you know, when there's no pressure. And so if this pressure goes down to 0, right, does that mean there's absolutely no pressure? No, we still have atmospheric pressure. We don't have a vacuum in here, in this line. If we had a vacuum that is a pressure lower than atmospheric, then gas would be sucked in. Does that make sense? No. There's an imbalance of pressures. And so this is the gauge pressure, but what is the absolute pressure? In terms of absolute pressure, then the absolute pressure that we have in that line, oops, let me get a different color pen here, is this. 14.9 plus 760 would be 774.9. So this is 774.9 millimeters of mercury liquid absolute pressure. Over here, what would the absolute pressure of this be? 0. This would be 0 millimeters of mercury absolute. And so when this gauge goes to 0, does that mean there's no more methane in here? No, it just means that the methane in here is at the same pressure as outside, and it's not going to be forced out. So we're going to have some kind of diffusion in, diffusion out type process happening. Let's do another example of this liquid pressure. Let's say somebody's down here at sea level. Actually, say somebody is here underwater at a depth, let's go at a depth of 9 feet. All right, what is the pressure there? What is the pressure at a depth of 9 feet in the ocean? Well, this person's going to have 9 feet of water. Right? 9 feet of water is going to exert some amount of pressure. But not only do they have 9 feet of water, they have thousands and thousands of feet of air that they're under. And so what we have to do is we have to combine the two, right? The pressure here is equal to the pressure of the liquid water plus the pressure of the atmosphere on top. The pressure of the atmosphere on top. Well, let's say it's an average day, and what's the pressure of the atmosphere that day? The pressure of the atmosphere is 1 atmosphere. And so we're going to do this in terms of atmosphere, not in terms of millimeters of mercury. And so how many atmospheres of pressure would this person be experiencing at that depth? And so we got all the weight of the atmosphere plus all the weight of the water, and so we just add those two up, right? Except the units don't add up, right? You know, the P total is equal to the weight of the atmosphere plus the weight of the water, liquid. And it's easy if the units worked out, but they don't, because the atmosphere is 1 atmosphere and this is 9 feet of H2O liquid. And so probably the easiest thing to do is to convert, you know, H2O liquid into HG liquid, and then from HG liquid convert that into atmospheres. So let's go ahead and do that. And so this term here, this is just dimensional analysis. So we go 9 feet of H2O liquid. And then we know that there's a conversion factor for this. And that is, in order to convert this from feet of H2O liquid, we just multiply the ratio of the densities. And I did it algebraically last time, but this time I'm just going to use a conversion factor. And that conversion factor is like this. The height is going to depend on the weight or the amount of the pressure. And so what we can do is we could just use this ratio to figure it out. And that ratio is this, 1.00. Oops, is that right? Yeah. 1.00 parts for every 13.59. Is that right? In other words, I'm going to need less mercury by this factor. Okay, or we could do it algebraically. Should we do it algebraically? Yeah, maybe we should do it algebraically. So the height of the mercury liquid is going to equal the density of the H2O liquid. Oops. I don't want height of, oh, I do want height of the mercury. Divided by the density of the mercury liquid times the height of the H2O liquid. And so this will give me in feet of mercury. And so the density of the H2O liquid is 1.00. The density of the mercury is 13.59. Now the units will cancel out here. Grams per milliliter. Grams per milliliter. And the height of the H2O was 9 feet. And so this will tell me the equivalent height in terms of mercury. So if I went swimming in a pool, you know, 9 feet deep, you feel the pressure, right? Water pressure. How deep, if you could swim in a mercury pool, how deep would you have to swim in a mercury pool to get that same? It would be hard to swim in a mercury pool because you wouldn't sink. Probably couldn't even break the surface. You'd float. Go ball. But anyway, here we would just do 1.00 over 13.59 times 9 feet, which gives us how many feet?
$0.66.
0.66. Give me another digit. 2. One more digit. 2. All right, we'll just carry extra digits. We aren't allowed. But if you could swim in a mercury pool, you'd only have to sink about a half a foot. You get the same pressure as being 9 feet deep in a water pool. Again, you wouldn't be able to sink because mercury is so dense and you're not dense enough. I guess you could put some weights, gold weights around your waist, something like that, and try to sink that way. All right, so we got 0.662 feet of mercury, and so we go from feet of mercury to inches of mercury, from inches of mercury to centimeters of mercury, and from centimeters of mercury we'll go to millimeters of mercury, and from millimeters of mercury we'll just go to atmospheres. And so can somebody do this for me? 0.6622 times 12 times 2.54 times 10 divided by 760. Zero point 265 atmospheres? Is that what people are getting? Mm-hmm. Yeah, all right. And so what we do here is this would be 1 atmosphere plus 0.265 atmospheres, which gives us 1.265 atmospheres, ignoring sig figs. And so about 1.3 atmospheres of pressure at that depth. The next thing is, barometer just measures the outside gas pressure, or the air pressure, you know. Air pressures fluctuate day to day, so barometric pressure fluctuates day to day, depending on weather, wind. Mm-hmm.
What's the pressure of that? Is that the pressure of mercury?
Yeah, this is the pressure of the water. The water. And so here, the person swimming here feels 0.265 atmospheres from the water, and then 1 atmosphere from the air. And so it's just combined. Yeah, the 0.265 is just from being under 9 feet of water. Under how many feet of water would the person have to be in order for it to be 1 atmosphere of liquid? This is a common question that's asked. I asked you, how tall would you have to build the barometer, right? And so a normal barometer has to be at least 760 millimeters tall. So if we have 760 millimeters of Hg liquid, that's 1 atmosphere, right? This is 1 atmosphere of liquid mercury. So if you're swimming under about 3/4 of a meter of liquid mercury, you would experience 1 atmosphere pressure. Now, if you had 1 atmosphere of air above you, that would be a total pressure of 2 atmospheres. Now, how tall would this be in terms of liquid water? In terms of liquid water, then it would be the opposite ratio. It would be 13.59 over 1.00. And so it would be about 13 times as tall. Is that right? 13 times as tall. So this is about 1 meter. Let's just round this grossly. 1 meter. So it would be about like 10 meters, 10 meters would be about 30 feet. 30 feet is about 3 stories. And so you'd have to be at a depth of about 30 feet in order of water to fill the same pressure as about 3 feet of mercury. Does that make sense? This is rough. You could calculate this much more accurately just by punching it in your calculator. Gas pressures are measured using a manometer, gas samples. And so let's take a look at a manometer here. This is a manometer. And so what you do is you trap a gas in this container and then you measure its pressure. Here, we measure by looking at the seesaw. In other words, what we're going to do is, if the seesaw is balanced like this, then the weight on the left of the seesaw is equal to the weight on the right of the seesaw. You see that? And so what's on the left? Well, what's on the left is the weight of the air, the barometric or the atmospheric pressure. What's the weight on the right? Well, the weight on the right is this gas that's trapped in the container. And so if the pressures are equal, then we run into this scenario where the pressure of the gas is equal to the barometric pressure. And so we just read the barometer and then we know what the pressure of the gas in this container is. This is liquid mercury here. Here, the seesaw is out of whack. Which side is heavier? The gas. The gas is much heavier. That means the gas has a much higher pressure. And so here we know that the gas pressure is greater than the barometric pressure. And here it's just the opposite. When we look at this seesaw, the barometric is much heavier than the gas. And so what we want to do is we want to figure out what is the gas pressure here. And I don't like this equation that they have because the equation doesn't... Petrucci does a strange thing. He hates negative signs for some reason. And so he tries to rearrange the equations so that they have positive signs. But sometimes the negative gives you a physical, visual picture of what's happening. Well, this equation I do differently because here, how do you make this equal? What you make this equal is you go, to the bottom edge here. We'll go to the bottom edge here. The weight of the gas is this, pushing down on the top surface of the mercury here. Well, what would the equivalent weight over here be? Well, the equivalent weight would be the weight of the atmosphere, and then you're under this much mercury. And so it would be the weight of this mercury. And so the pressure, if you were here, would be the weight of this column of liquid mercury plus the weight of the air. Does that make sense? And so this is the way I rearrange this equation. And it makes, to me, this makes a lot more sense this way if I just rearrange it like this. And so we're looking at our manometer. This is called a manometer here. And we see that the two liquid levels are in balance here. And so what we do is we just set it equal like this. And so the pressure of the gas here, will be the same as the pressure of the liquid mercury here, plus the pressure of the air here, the barometric pressure. And so we have to add these two up, and then they'll equal the pressure of the gas. So we just say that the pressure of the gas is equal to the pressure of the barometer plus the pressure of the liquid mercury. Well, hopefully the units are the same. This is why using liquid mercury is so convenient, because when we measure the barometer, what are the units of the barometer? The barometer is in millimeters of Hg liquid. The pressure of the liquid mercury, all we do is we put a scale here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We just measured this. How many millimeters do we have? Well, we start off at 0 here and then measure it. So let's say we had 20, looks like 20.5 millimeters of mercury, 20.5 millimeters of mercury. And then we go out to the barometer and measure the barometric pressure that day, and then just add the two together. Does that make sense? There. All right, now let's look at this one. This is where Petrucci does something weird, because you take a look at this, and you know, both these equations are the same, but the way that you define delta P is here. Petrucci says delta P is positive here, and then over here, Petrucci says delta P is negative here. I don't care which way you do it, but usually when I measure the height is always positive. I never measure negative height. Okay. But it's okay, whatever you want to do. I guess in a way it's negative, but I don't think that way. And so, where I'm going to differ in Petrucci is how he does this one. And so let's take a look at this one. And you use whatever way you want, I don't care. But in this case, the weight of the atmosphere is greater than the weight of the gas. Here, you know, the weight of the gas, the pressure of the gas is greater than the pressure of the atmosphere. Here, the pressure of the gas is going to be less than the pressure of the atmosphere. Now, we can see that, you know, obviously the seesaw's heavily tilted. But what we're going to do is we're going to figure out, well, over here we got the weight of the atmosphere. What would the equivalent weight over here at this depth? And so at this depth we have the pressure of the gas plus the pressure of this liquid, column mercury here. And so what we say here is this, that the pressure of the barometer is equal to the pressure of the gas plus the pressure of the mercury liquid. And so here we have the pressure of the barometer, okay, weighs down over here. And then over here we got the pressure of the liquid, mercury, plus the pressure of the gas. And so we combine those two. And therefore, if we solve for the pressure of the pressure of the gas is equal to the barometric pressure minus the pressure of the liquid mercury. So my difference here is Petrucci hates negatives in equations, so he defined delta P differently. I define delta P the same for both, and then just have a negative sign in the equation. You'll see him do this on a number of equations, which I just say forget it, because you know, some of the other equations he does like this are ones that, you know, it's final minus initial, but he'll write initial plus final or something like that. You know, just to get rid of something. All right, that's how you measure gas pressures using a manometer. Manometers are very common. They have manometers filled with mercury, they have manometers filled with water. You know, the manometers filled with water are big. Because, you know, when you're measuring house pressure, house gas pressure, you only need like 8 inches, right? 10 inches, 12 inches, a couple of feet, you know, for liquid water. So you can make one of these pretty easily. All right, what else do we have in this chapter? What else we have in this chapter are things like the simple gas laws. You remember the simple gas laws? Oh, actually, let me talk about the units of pressure first. So I didn't go through this that clearly. The standard unit of pressure that we use is atmosphere, but it isn't the standard unit internationally. Do you know what the standard is internationally? Pascals is inconvenient because Pascals is times 10 to the 5th, which is just a hassle. And so what they do is they convert Pascals into bar. You know, 1 atmosphere is 1 times 10 to the 5th Pascals. Or actually, is that 5th? 1, 2, 3, 4, 5. Yeah, 1 times 10 to the 5th Pascals. 1 atmosphere is 1 times 10 to the 5th. 10 to the 5th Pascals is a hassle to say all the time. And not only that, it's not really 1 times 10, it's 101,325. So 1.01325 times 10 to the 5th Pascals. Well, it'd be easier to talk in kilopascals, but kilopascals is still a hassle because it's 101. And so they define a new one. They call a bar 1 bar is 1.01325 times 10 to the 5th pascals. And so a bar and a pascal is the same thing, except now bar is just, and so in other words, atmospheric pressure is about 1 bar. And so an atmosphere and a bar are about the same, but the bar is the international standard because it's based on physics. Pascals are based on physics, like kilograms, meters, seconds, this kind of stuff. Atmospheres is just whatever, somebody, I don't know, how did the atmosphere come out? Somebody there every day measuring the pressure. What's the weight of the atmosphere? And then averaging it. It fluctuates all the time. So here we go. All right, so these are the units here. We're going to use both bar and atmosphere. So we have to get comfortable with both. Bar and atmospheres. A bar and an atmosphere are very close, almost the same thing. 1 atmosphere is about 1 bar. Just slightly different. The bar is a little bit smaller, a little bit bigger. A little bit bigger? All right. Now, in this chapter, we do the simple gas laws. Do you remember Boyle's law? Yes or no? No? Okay. Boyle's law you don't have to remember. Do you remember Charles' law? No? You don't have to remember it either. Do you remember Avogadro's or Gay-Lussac's law? You don't have to remember that either. You don't have to remember these because all these laws, all the simple laws are contained in something you do have to remember, and that something you do have to remember is the ideal gas law or the universal gas law. And so let's talk about that. $22.4 liters. Have you heard that number before? You guys have that memorized? 22.4 liters? What did that refer to? 22.4 liters. Molar volume. All right, let's look at the combined. This is what you do have to remember, but this is easy to remember, right? Everybody has this memorized. And so the equations with this are pretty straightforward. PV equals nRT, or you could have PV over RT, or no, we don't want PV over NT. PV over NT is equal to R, which is equal to constant. And so what we could have is P initial, V initial, N initial, T initial is equal to P final, V final, N final, T final, which is equal to R, constant. And so we have this one and we have this one, which we use. The only difference here is in Chem 4, they don't change the moles. They always leave the moles fixed. In Chem 1A, sometimes we change the number of moles, see what happens to the pressure, right? Or whatever. Well, do you have this memorized? You should have this one memorized. 0.08206. What is it? 0.0820. A lot of people have this memorized from Chem 4. 0.0821. They round this. But we're going to be a little bit more precise in this class. I want you to memorize R with atmospheres to 0.08206. It's a little bit better. So we have 4 sig figs. Do you know it to bars? To bars, it's 0.08315. 8315 to 4 sig figs, right? If we round it. This bars is becoming more and more important, so this one's actually a pretty good one to memorize too. But it's okay if you don't have it memorized. You guys have it memorized, the atmospheres? Well, you know, we can always derive it. Because we're always given it. And so if we know it's 0.08206 liters times atmosphere per mole Kelvin, and then we know that there's 1.01, what was it, 1.01325? Yeah, 1.01325 bars per atmosphere. And then the atmospheres cancel and it gives us. So if you remember 1.01325 from pascals, then you can derive it. In other words, normal atmospheric pressure is 1 atmosphere or 1.01325 bars. That's normal atmospheric pressure. These others you don't have to memorize, except for this one I want you to memorize. 8.3145 joules per mole Kelvin. 8.3145 joules per mole Kelvin is the thermodynamic bar value that we use a lot for calculations. Which one you use depends on the units of your equation. And so these aren't that difficult, you know, these problems. You know, there's variations of this. You know, the variations of this equation that we can derive, for example, the density of a gas. The density of the gas is equal to the mass of the gas over the volume of the gas. The mass of the gas is just grams. The volume we can use the ideal gas law to calculate. PV equals nRT, so V equals nRT over P. And so this means we get the mass times the pressure over nRT. The mass over N, that would be grams, N would be moles, grams per mole is the molar mass. And so this is equal to the molar mass, we'll abbreviate like this, MM, molar mass times P over RT. Well, we can figure out the density without having to do any measurements here. All we need is the molar mass of the gas. The molar mass, we can calculate the density at any pressure and temperature we want. And so if you want to know the density of nitrogen at 10 atmospheres and 100 degrees C, you can do it without doing any experiments. Right? And so this equation is quite useful, density of the gas. What else did you calculate? What else have you calculated? Other very common calculations are this, the volume over N. The volume over N is called the molar volume. And the volume over N, the molar volume, well, V over N is equal to RT over P. We just rearranged this equation. V divided by both sides by N divided both sides by P, we get this, RT over P. And so we can calculate the molar volume of a gas at any temperature and any pressure. The common one is at STP. At STP, remind me what STP is. 0 degrees C and 1 atmosphere. 22.4 liters per mole. But STP is kind of inconvenient because do you work in a 0 degrees C lab? Oh, it's very inconvenient. And so what we want is we want it at 25 degrees C. In fact, don't even bother memorizing this. We're never going to use it. I memorized this when I was a student, and I never used it, not once. You might see it on a standardized test or something, but you'd use this a lot more. At 25 degrees C in 1 atmosphere, what is the molar volume of the gas? So plug in R, which would be 0.08206, times T, which would be 298 Kelvin, divided by P, 1. And so can somebody punch this out, 0.08206 times 298? Tell me what they get. 24.5. Give me one more digit.
24.45.
24.45 liters per mole. That's going to be about 24.5 liters per mole of gas in this room. This is much more useful. In other words, if we really want to round it, it's about 25 liters of gas per mole. Molar volume, that's kind of useful. What else is useful that we get? We also get the molar mass of the gas sometimes. The molar mass of the gas. The molar mass of the gas is equal to the mass over N. We could rearrange N here, substitute, and so N is equal to PV over RT, so we go PV over RT, and we go mass times RT over PV. And then we see mass over volume is equal to the density. So this is the density of the gas times RT over P, or we could have rearranged this equation too, one above it. But those are some common equations that we use with this. Okay. And so the calculations are in the back. Applying the ideal gas law. Applications of the ideal gas law. Determining molar mass, determining density. Okay, let's talk about gases in chemical reactions. Stoichiometry, gas stoichiometry. Next. Etc. You know, the law. Gas stoichiometry, you know, at the heart of the stoichiometry map is a mole-to-mole conversion. You know, we go from moles of something to moles of something else using the balanced chemical equation or the formula. And so a mole-to-mole conversion. When we have gases, we can go straight. And so usually what we measure in a gas is what? We normally measure, do we normally measure the grams of gas that we have? Do a gram to mole conversion? No, because measuring grams of gas is not easy because of buoyancy effects, you know, in air. So it's hard if you have a sample of gas to measure. Sometimes you can. If you cram a whole bunch of gas into a cylinder, you know, if you cram a whole bunch of gas into a cylinder, you can take the weight of the cylinder before and take the weight of the cylinder after, and then you can have grams of gas in a heavy metal cylinder. But normally what we measure is we measure the volume of gas A. And so the volume of A gas. And so we have two choices here. One, well, we just use N is equal to PV over RT. You know, we just calculate the moles using the ideal gas law. So this would be algebraic. Or two, we use the molar volume as a conversion factor. And so use molar volume, MV. Stands for molar volume. sometimes it's convenient because if you do all your reactions at 25 degrees C, then you might as well just memorize the molar volume of the gas. You know, for example, at 25 degrees C in 1 atmosphere, which is the most common, right? At 25 degrees C in 1 atmosphere, you know, how many liters in a mole? There are 24.45 liters in a mole. Or in other words, 1 mole of gas contains 24.45 liters. If you're at 0 degrees C in 1 atmosphere, we could use that other one. So this is just an easy conversion. This is why I asked you to memorize this one. I asked you to memorize this one because if you look at most of the homework problems, what's the temperature? 25 degrees C. What's the pressure? 1 atmosphere. And so might as well memorize it. And if you look at, you know what? I bet you won't find one problem at one gas stoichiometry problem at 0 degrees C. Not one. Not one. And so that's what I found. I found this one's a good one to memorize. The other one, forget it. Okay. But sometimes the pressure is not 1 atmosphere. Sometimes the temperature is not 1 atmosphere. But you know what? This calculation is so easy because the molar volume of the gas is just equal to, what is it equal to? Well, the molar volume of the gas is equal to V over N, which is just equal to RT over P. How quickly can you calculate RT over P? It's a quick calculation. Well, this is very quick too. So either way, but the thing is, sometimes we have to go on the outside here. So for example, if we go from moles of B to volume of B gas, then, you know what? Then it makes total sense to get the molar volume because you can just reuse that same conversion factor over there. If B gas is at the same temperature and pressure, which it is when you're doing stoichiometry. You know, they rarely change the input temperature and pressure and the output. They don't say, okay, we're going to freeze it going in and then we're going to rapidly warm it up going out. No, they don't usually do that. They just say, okay, you're working in a lab. The lab is fixed temperature and pressure. And so what goes in comes out. Sometimes we work with mixtures. Here. And so sometimes we work, you know, with mixtures like, you know, volume of a mixture. If we have volume of a mixture, then we need something like a composition. But when we have compositions, we always have to be careful because is the composition, you know, typically the composition is going to be percent. Is the composition percent by mass or is it percent by mole? That's very important to know, you know, because when you're dealing with gases, you don't know sometimes what they're talking about. With gases, we have other ones too. We have percent by mass, we have percent by mole, we have percent by pressure, we have percent by volume. We have all these percentages. We have to figure out which percentage we need to use for this. So this is brings us to the next. Actually, I need to do something for that. This brings us to the next topic, which I'm going to combine. Combine this. When we're doing a chemical reaction, we're looking at a gas mixture, basically. So let's see a chemical reaction that consists of a gas mixture. For example, here, if you look at this reaction, let me back up one page. this reaction, we have this nitrogen monoxide or nitric oxide and oxygen. It's a gas mixture. It's also a chemical reaction because the nitrogen monoxide and the oxygen react together. And so automatically, every time we have a reaction involving gases, is going to be a gas mixture. And therefore, you have to know, when you're dealing with mixtures, you know, what ratio you mix these in. And so here, in this case, do I mix these in a ratio of 2 grams to 1 gram? 2 grams to 1 gram? No, because chemical reactions are not mass mixtures. Chemical reactions are mole. And that's always fixed. And so this would be 2 moles to 1 mole. 2 moles to 1 mole. And so automatically, this mixture, we automatically think in terms of mole percentages, not mass percentages, because chemical reactions are not mass ratios, they are mole ratios. Okay, now we got to think about other things as well. Could I mix this in terms of pressure? Could I put 2 atmospheres of NO and 1 atmosphere of O2? Would that work? 2 atmospheres of NO and 1 atmosphere of O2. Is that correct or incorrect? Would that work? Answer is yes, that would work. Or what if I did this? If I did 2 liters and 1 liter, I take 2 liters of NO and 1 liter of O2, is that true? Would that work too? Not always, that's correct. And so we have to learn about mixtures and dealing with mixtures. And so I'm going to take a mixture of nitrogen and oxygen. Okay, stoichiometrically, this is always true. I need 2 moles of nitrogen and 1 mole of oxygen always, right? Always. This is true. Now, there are 2 ways to visualize that. And so the mole ratio is always going to be the same. You know, 2/3 of the moles will be nitrogen, 1/3 of the moles will be oxygen. So it's a 2 to 1 ratio. This is always true. And so the mole ratio is always going to be the same. And so the mole percentage will always be the same. You know, the mole percentage this is going to be 66.7% by mole nitrogen. This is going to be 33.3% by mole oxygen. This is fixed. This is not the same as the mass percent, right? This does not equal the percent by mass. The percent by mass would be different because they weigh different amounts, right? And so it's not equal to percent by mass. Well, we have two standard ways of visualizing mixtures, gas mixtures. The 2 standard ways of visualizing gas mixtures is one, we visualize a gas mixture by using Dalton's law. You heard of Dalton's law? Dalton's law. Dalton's law says this. Okay, I'm going to take, you know what? I'm going to cram this into this. So how to visualize this? Okay, 2 ways. 2 moles of nitrogen is about how many liters at room temperature, 25 degrees C and 1 atmosphere. We're just going to call it roughly about 50 liters. 1 mole of oxygen is about how many liters? 25 liters. And gases are expandable and compressible, so we can have it any liters we want. Pressure is going to vary. And so one way of visualizing this is we have 50 liters of nitrogen and 25 liters of oxygen, right? And so the first way we'll talk about is by Avogadro's mixture. An Avogadro's mixture will tell me how many liters of gas will I end up in this mixture. I'm going to end up with 75 liters. And so I'll end up with 75 liters of a mixture of N2 and O2. And that 75 liters consists of 50 liters of nitrogen and 25 liters of oxygen. Okay. In Dalton's law, or Dalton's mixture, in a Dalton's mixture, I'm going to end up with 25 liters of gas, of mixture. I end up with 25 liters of nitrogen and oxygen, but the nitrogen will be at twice the pressure. And so this comes out to 25 liters of nitrogen, oops, not 25, 50 liters of nitrogen and 25 liters of oxygen. Over here, the oxygen will come out at 1 atmosphere of pressure, but the nitrogen will come out at double the pressure, 2 atmospheres, because we're compressing it into half the volume. And so altogether, I get 3 atmospheres of gas pressure. Dalton's. I don't like how Petrucci has it in his book. And so let's look at another one. The way Petrucci has it is this equation 616. Do you see this equation here? This is called Dalton's law of partial pressures. Do you see this equation here? This is Avogadro's law of partial volumes. And so these 2 equations are important, but he doesn't even give a number to Avogadro's. He completely ignores it. And so we aren't going to ignore it. We're going to consider it. And so let's just look at air for right now. The next example is air. Let's say I have 1 liter of air. 1.0 liters of air at 25 degrees C and 1 atmospheric pressure. What's in this air? Well, air consists mostly of nitrogen. What is the percent nitrogen in air? Okay. What is the percent oxygen in air? So we're going to round it. Yeah. So we're going to say that this is 80% nitrogen and 20% oxygen. And so air consists of 80% nitrogen, 20% oxygen. Okay. Is that by mass or by mole? So what is that by? Is air 80% nitrogen by mass or by mole? What do you think makes more sense? Should we weigh 100 grams of air and call it 80 grams of nitrogen, 20 grams of oxygen? Or should we just get a bunch of air and see, you know, 80% of the molecules of air are nitrogen, 20% of the molecules of air are oxygen? Which one makes more sense? Well, it depends on who you talk to. You don't know, right, until somebody tells you. Well, this is by mole. And so 80% of the molecules are nitrogen molecules, 20% are oxygen molecules. That's fixed. And so mole percentages are fixed. But pressure and volume percentages are not fixed. So if I have 80% nitrogen, does that mean I have 0.8 or 80% of 1 atmosphere? It would be 0.8 atmospheres. Does that mean I have 0.8 atmospheres of nitrogen and 0.2 atmospheres of oxygen? True or false? In this 1 liter at 1 atmosphere, I have 0.8 atmospheres of nitrogen and 0.2 atmospheres of oxygen. This is called the Dalton's law of partial pressures. And you'd say it's true because Dalton's law of partial pressure says the total pressure, 1 atmosphere, has to be the partial pressure of each of the gases. And so when I look at the gas, nitrogen, which will have as blue, and oxygen will have as red. Nitrogen, there's 80% more molecules, so there's going to be 80% more, I mean, you know, a lot more collisions here, basically. 20% of the molecules are oxygen. And so for every 8 collisions of the nitrogen, I get 2 collisions of oxygen, which means that all those combined collisions are 1 atmosphere. So 80% of that 1 atmosphere comes from the nitrogen collisions, 20% comes from the oxygen collisions. So in other words, that's true. 0.8 atmospheres worth of nitrogen, 0.2 atmospheres worth of oxygen. Okay. But the next thing is, okay, how many liters of nitrogen are in this box? How many liters of nitrogen? I want to fill this box. How many liters of nitrogen should I measure out? And how many liters of oxygen should I measure out? Well, it depends on your perspective. Should I weigh? Oh, but you know, 80% of the molecules here, so that means I need 0.8 liters. 0.8 liters of nitrogen, 0.2 liters of oxygen. True or false? It's true. The thing is, this is why I'm bringing this up. The reason I'm bringing this up is because people get the two mixed up all the time. If you think Daltons, you have to stick with Daltons. If you think Avogadros, you have to stick with Avogadros, but you can't mix the two. They don't mix. And so basically there are 2 ways of thinking about this. In terms of Daltons, we have this. How many liters of nitrogen do we have? We have 1 liter. And so we have 1.0 liters of nitrogen. But the nitrogen is, there's no oxygen in here, we're just looking at the nitrogen collisions. The nitrogen will be at 0.8 atmospheres. And we're going to have how much oxygen? Well, we're going to have 1.0 liters of oxygen, but the oxygen is going to be at 0.2 atmospheres. And so one way of visualizing this gas mixture is this. We put all the nitrogen in a 1 liter box and measure its pressure, it's going to be less. And then we put the oxygen in a box, 1 liter box, and measure its pressure. Pressure is going to be quite a bit less because there's quite a bit fewer oxygen molecules. And so this is called the Dalton's addition. And that is the partial pressures, you know, the pressure of this is 0.8, the pressure of nitrogen, 0.8 atmospheres. The pressure of oxygen is 0.2 atmospheres. And so if we combine the partial pressures, we get the total pressure. The total pressure is 1 atmosphere. But the volumes are this. This is the volume of nitrogen here, which is 1 liter. This is the volume of oxygen. So when we combine 1 liter of nitrogen plus 1 liter of oxygen, what is V total? What is V total? If I add 1 liter of nitrogen to 1 liter of oxygen, what's my total volume? You would think 2 liters, but 2 liters is wrong. It is not 2 liters. What is it? 1 liter. It's 1 liter. And so 1 liter of nitrogen plus 1 liter of oxygen yields 1 liter of gas mixture. Okay. This is Dalton's. On the other hand, we have Avogadros. In Avogadros, it's the same mixture, but we visualize it differently. In Avogadros, we don't have 1 liter of nitrogen. We have 0.8 liters of nitrogen. But the 0.8 liters, we compress the nitrogen into a smaller box so that the pressure, you know, the number of collisions per unit area is the same as before. I mean, not the same as before, is now equal to, okay, make some room here. The pressure of the nitrogen is 1 atmosphere now, 1.0 atmosphere. Plus, we're going to add a 0.2 liter box of oxygen. When we add a 0.2 liter box of oxygen, now we compress the volume so that the gas collisions will be equivalent to 1 atmosphere. So the pressure of the oxygen here, the partial pressure of the oxygen is 1.0 atmospheres. And so in Avogadro's addition, what we have is 0.8 liters plus 0.2 liters gives us a total volume of what? In other words, the partial volume of nitrogen plus the partial volume of oxygen is equal to V total. And so in this case, V total is 1.0 liters. Now we add up the partial pressure of nitrogen plus the partial pressure of the oxygen is going to equal what? It's not going to equal 2.0 atmospheres. It's going to equal 1 atmosphere. And so where Dalton's law is valid, Avogadro's would be false. Where Avogadro's is true, Dalton's law would be false. And so we summarize that here in equation 617. In equation 617, we summarize it like this. This is called the mole fraction. The mole fraction of the mole percentage. I mean, if you take the mole fraction and times it by 100%, you'll get the mole percentage. And so the mole fraction, the moles of A over the total moles, this is always true. It's the mole ratio. It's always true. Regardless of what the pressure or volume is. The mole fraction is always true. But the pressure fraction, you know, the partial pressure of A over B total, this is true, this is Dalton's, this is true only at constant, true only for constant what? Volume conditions. The volume cannot change. And so here we see the volume doesn't change. 1 liter, 1 liter, 1 liter, everything's 1 liter. So if I have 1 liter of mixture, how much A do I have in that 1 liter? 1 liter of A. How much B do I have? 1 liter of B. How much C? 1 liter. Everything's 1 liter. If it's 1 liter. The volume fraction is Avogadro's law. This is Avogadro's. This is true only for constant pressure. The pressure of everything is going to be the same. Each component of the mixture will have the exact same pressure. How many atmospheres of nitrogen do I have? 1 atmosphere. How many atmospheres of oxygen? 1 atmosphere. How many atmospheres of CO2? There's CO2 in air. How many atmospheres of CO2 do I have in the air? How many atmospheres of CO2 are in this room? 1 atmosphere. If I'm talking about Avogadro's. If I'm talking about Dalton's, then how many atmospheres of CO2 do I have in this room? Well, it's not 1 atmosphere. It's going to be way, way, way less.